Okay, good morning, everybody. So there's a question about when will the M1 document be posted. It should be late this week. I'm still working on it. So today we're going to talk about STL iterators, which are essentially a generalization of pointers. And they're really useful with the container classes. You already saw vector. You're going to see some more of those today. And iterators are an important part of how you interact with those container classes, how you say, which element am I talking about? Okay, so last tutorial we talked about C++ templates. There were two types. There were function templates. We went through the examples of swap and minimum. And there were class templates, and went through the example of the pair class. And so templates, again, are recipes for how do I create functions or create classes that work for a whole range of data types. They are a little harder to write than normal C++ code, but the creators of the standard template library have created a very powerful library for you, which is very convenient to use. And the most important part, in my opinion, of the standard template library is what's called the container classes, and we looked at one of those last week, vector. The container classes are basically key data structures that work for any kind of data you want to store because the data is templated. So what are we going to talk about today? Well, we're going to have two 1-hour sessions or two 50-minute sessions. The first one, we're going to talk about what an iterator is, what operations can you perform on it, and iterators, as I said, are useful for indicating what element in a container you are working with. We're going to, once we know iterators, we can now start working with more containers than just vectors. So we're going to look at the list container that's part of the STL library, and what it's good for and what it's not so good for compared to a vector. And as usual, if you have questions, just put your hand up or type in the chat. Okay, so what's an iterator? It identifies an element in a container. So it's similar to a pointer. And the way that an iterator, the way you interact with it, the operations you do on it, should be very familiar because they're made to look like pointer operations. Often an iterator actually, it's a class, but often its implementation has a pointer inside of it. Sometimes its implementation has more than a single pointer inside of it. Doesn't matter. From your point of view, you don't really care. That was the standard library creator's problem. You just use the operations they've exposed, which look like the operations you can do with a pointer. So it allows you to identify an element in a container, allows you to access an element in a container. Again, that's like a pointer. It allows you to move between elements in a container, which is similar to pointer arithmetic. So do people know what pointer arithmetic is? Have you ever seen pointer arithmetic in C or C++? So you can type a yes or no in the chat. Okay, some people, I see at least one person saying yeah. Okay, anybody else? Two gives me more faith. Again, pointer arithmetic are things like this. You can say p++, and that increments a pointer. And it actually increments a pointer by enough to point at the next object. So if I had an object that was 8 bytes, and I said p++, and I have an array of objects that are size 8 bytes, and I say p++, I actually move the pointer 8 bytes forward or up in memory. I'll point at the next thing. So in C and C++, you can already do that. We're going to use that syntax. That's what, again, iterators are made to look just like pointers because they are essentially a generalization of pointers. The last thing is the creators of the STL always try to make your code fast. So iterators are restricted to efficient operations. If something would be really slow to do with an iterator, but theoretically possible for the creators of STL to make work, they just won't do it. They will not make that method, and you'll get a compile time error if you try to use it. And that's done as a favor to you so that it's harder for you to write really slow code. Okay, so let's compare the iterators to operator square bracket. Operator square bracket is indexing. We can use it with arrays, we can use it with vectors. And we used it with vectors last week, and it worked fine. So why can't we just use that? Why do we need to have iterators which are like pointers at all? It's basically not all of the container classes are going to give us this indexing or square bracket operator. That square bracket operator implies random access. Think of an array. You can ask for entry 2, you can ask for entry 1,000,000. They both take the same amount of time to return. Basically, they're both order one operations. So they imply random access. Not all containers have random access, so this syntax doesn't work, doesn't make sense for a bunch of them. So in the standard template library, all containers have iterators defined. Each of these iterator types are different. So they all behave very similarly. They present the same operations or a subset of the same operations. But when you want to make an iterator to go through a vector of integers, you have to ask for the right type of iterator. So you say, I want an iterator. And this colon colon is called the scope resolution operator in C++. What this means is it says, I want you to look for a type, a class basically, that is defined inside the vector templated class, and I want the version for an integer. So that's what this whole thing means. Give me the iterator that goes with a vector of integers. This says, give me the iterator that goes with a vector of floating point numbers. This says, give me the iterator that goes with a list of integers. Okay, so let's just review what we already know about the first container class you looked at, vector. So we saw that we could access elements, read them, we're using the square bracket operator. We can actually also modify them, so we can change them using the square bracket operator. We can add things to the end of the vector, make it bigger, and put the element in with pushback. And we can ask how many elements it has by asking, querying the size member function. All of these are fast. They're order one. Today we're going to learn some new functions. We're going to learn a function called begin, and begin is called on a container class, so it's a member function of a container class, and it returns an iterator to the first element in that container class. And there's a matching function called end. Again, you call that with an object that is from one of these container classes, and it returns an iterator to the element that is just past the end of the container. So there's nothing there, but it's like it indicates I'm just past the end of the container. And you use that for bounds checking. So you can do things like write for loops that go through a whole container. Okay, so where does begin and end? So let's say I've declared a vector of integers. I called it my vector. If I call it size member function, it returns n. So that means it has n elements, and their indices would go from 0 to n minus 1, just like an array. If we call begin, it's going to point at the first element. So it's an iterator, and again, it's like a pointer. So it points at the first element, and end is going to point just past the end of the vector. There's nothing there. You shouldn't try to access end. You use it to check, am I done yet? Okay, hopefully that all makes sense. Okay, so I haven't really told you all the rules about iterators, but I've told you that they're a generalization of pointers. So but they're a generalization of a pointer that works only, you basically use it to go through a single container. Okay, so unlike pointers, which can be used to point at sort of arbitrary memory addresses, iterators are used to walk through pointers, or walk through a container. So we can do things like set it to the start of the container and walk through until we get to the end. Okay, so given that, I want you to look at this code. I basically have created a vector of integers, called it numbers, and I've initialized it with four values. So its size will be 4, and the 4 things in it will be 1, 2, 3, 4. I want you to go through these lines of code. I'm going to launch a poll and just say whether you think each of these lines will compile. Will it be allowed and do something? And I haven't actually, this is an exercise in guessing because I haven't actually told you all the rules yet. But basically, if the iterator does, if it appears it would do something useful that you could do with a pointer, then it's going to compile. That's the basic rule. If you look at it and go, this doesn't seem to make any sense, then it's not going to compile. So that's pretty vague spec, but we'll do a knowledge gap here and made to stick terms, and I want to see if you can guess which of these are going to work and which aren't. And then we'll go through in a couple minutes and I'll tell you which ones work and which ones don't and what they do. Okay, so go ahead and start filling out those questions. Take your best shot at each of these things. Okay, so most people have answered. I'm going to give you another minute, so if you haven't answered yet, try to go through them and post your answers. Okay, so I'm going to close the poll, so you got a few seconds left. And 5, 4, 3, 2, 1, and we're closing it down. Okay, so let's see what everybody thought. Hopefully you can see the poll. Can you see the poll now with the results? Okay, great. Okay, so the first one, we've got an iterator that we've declared. It's of the right type. So it is the iterator that goes with a vector of integers that matches what we declared for our container class. That looks good. And we set it equal to numbers, which is the name of this object, a container of type vector of integers. And we say set it to the beginning of that. Make it point at the beginning. 93% of you thought that would compile, and that's right. That's going to compile. It's going to point to the start of the vector. So it's going to point right there. So it's pointing at index 0 where there's the value 1. Okay, case 2. So will IT equals 5 work? And 67% of you thought it won't work, and you're right. This one will not compile. Basically, it's the wrong type. 5 is an integer. It's not an iterator, so C++ is going to say these types don't match. And it basically doesn't really make sense. It's like, well, what does that mean? Does that mean point at memory address 5? We have a container here, not we can't put in arbitrary addresses. I don't know what 5 means. Okay, so that won't compile. Next one, case 3 is increment the iterator, and yeah, 96% of you said that'll compile, and that's right. That is, it makes it point to the next element. So we were pointing at entry, well, the first entry, which has the number 1. After that line, the iterator will be updated, and it'll now point at the second entry, which has the number, well, index 1 and the number 2 in it. Okay, IT minus minus, and basically the same. 96% of you said that's going to compile, and that's exactly right. Just moves the iterator back. So it was pointing at 2. Now it's going to go back. It's going to point at 1 again. Let's see. Int x equals star IT. So let's see. 80% of you thought that would compile. So if it's a pointer, that would work. That's dereference. Means I want the value that it points at. And yeah, it does work. So it basically says x should be whatever this pointer points at. Pointer points at the number 1, so x will become 1. Okay. Iterator not equal to numbers.end. Numbers.end again is like a flag value that is kind of out here past the end of the vector. And let's see, 65% of you said that will compile, and yeah, that will work. That's how you check, am I pointing at a valid element? If you write a for loop that walks through this container, that's how you're going to see, am I at the end or not? If this returns false, it means I'm not at the end. What about IT less than numbers.end? So this one, the class was evenly split, 50-50. So this will compile. Okay, so for a vector, the iterators essentially, they understand the order of the vector. So they know I'm pointing at index 0, and that is before the end of this vector. So it will actually return true in this case. And it works. Okay, so I think I revealed one more already, and that's basically star IT equals 27. Okay, so let's erase this stuff. This is where my iterator is pointing. It's pointing, that's where we left it, right there. So 78% of you thought that that would compile, and yeah, it will compile. So what it's going to do is it's going to set this value, index 0, to 27. Just like with a pointer. You can use the dereference. Dereference again means what I'm pointing to. So it says change what I am pointing to the number 27. That works fine because this is a vector of integers. All the types work. We just do it. Okay, the last one. Iterator equals numbers.begin plus 2. And 87% of you thought that that would compile, and that's right. So it basically says skip over 2 elements. So the iterator was pointing at index 0. It's now going to point to the number 3, which is at index 2. So most of these compile. Okay, so I'm going to stop sharing this. Any questions on this, or is that all pretty clear? Okay, I'm going to take that as clarity. So, what if you increment past the number of elements? Yeah, good question. So you shouldn't do that. It's like going past the end of the array. If you increment past the number of elements, let's say I just kept doing this. I kept going IT plus plus over and over again. So I went there, then I went there, then I went there. I won't crash. Nothing bad will happen if I iterate past the end, as long as I don't try to do anything with the iterator. If I actually try to dereference it, then something bad will happen. I might crash, but it certainly doesn't make any sense. So I don't want to increment past the end. I should be checking before I do an increment, I should check if I'm at the end. Okay, so if I should do this check before I do an increment, so that I don't go past the end. And again, if I go past the end, it won't be bad until I try to use, well, for a vector at least, until I try to use the iterator. But you should just not go past the end. Okay? And yeah, there's a question, do 6 and 7 return bool? They do. Those are both for Boolean tests. Yes, there's a question, so the vector initialized under iterator is a pointer. The iterator for a vector, if you actually go look inside the standard library, you're going to see that the private data is in fact a pointer. Because if you think about everything I've done here, you can make all of this work with function calls that are wrapped, like their data is a pointer. So for a vector, there really is a pointer under the hood. It's kind of hidden from you by all of these member functions. For some other container classes, the iterator can be more, its actual private data can be more complicated than just a pointer. You don't care because you don't actually care how it's implemented. You just care about what the interface is. But for those curious, yes, that is how the vector iterator is done. Okay, so how do we loop through a vector? So we learned how to do this last week with indices. So let's just review that. Size t is just a big integer. Okay, so you could just change this to int. There's some C++ coders, including one of my tutorial TAs who helped make these slides, likes using size t, which is basically maps to an integer, but you can just think of that as integer. So what does this do? It says for index 0, I is my index variable, so for I equals 0, I less than the size of the vector, keep incrementing I, and access my vector numbers with that index I and print it out. So this is going to print out 4 numbers. That's going to print out my vector. And you hopefully remember how to do that from last week. We can rewrite this now using iterators. So instead of indices, we can do the same thing. The code is slightly longer. We basically say, I want an iterator, so I'm going to call it IT. I have to say what the type is, and the type's a bit long. It's an iterator, and the type of iterator I want is the iterator that goes with a vector of integers, because that's the kind of container that I'm going through. I set it equal to, to point at the start of my vector. So my vector is called numbers, so I say numbers.begin. I'm going to loop through as long as I'm not at the end point, right? Remember, end is after the end of the vector. So if I ever have the iterator equal to numbers.end, I'm done. I should stop. I should not access this iterator anymore. I've made it, done everything. I've done all the elements already. If I'm not at the end, I'm going to increment the iterator. Okay? So, and every time I go through this loop, I'm going to print out the element that I'm pointing at. So I start out pointing at 1. First time through the loop, I print out what I'm pointing at with this dereference the iterator. Then I'm going to come through the loop, go back up. I'm going to check I'm at the end. So let me erase some of this stuff. So I go back through the loop. I check, am I at the end? I'm not, right? The end is out here. Oops. So I'm going to increment the iterator. So now the iterator points there. And I'm going to print out what the iterator is pointing at. So I'm going to print 2. I'm going to keep doing this. So I'm going to keep going through. I'm going to keep updating my iterator. And eventually I will update the iterator so that the iterator is actually here. This test returns false. The iterator is equal to numbers.end. So I break out of the loop and I'm done. Okay, so that's how I can walk through a vector with an iterator and print it out. I see a good question. There's basically, this type looks kind of complicated. It is. It's not hard to learn this syntax, but it is a bit of a long name. So the question is, could you have used the word auto instead? Okay, so what do you think? Could the compiler figure out the type? One of the ways you can learn more about a programming language like C++ is if you actually think about what can the compiler do and what can't it do. So can the compiler figure out what type I want for IT here? If it can, then I can use auto. So could it figure out, auto is this keyword that just says, as we talked about last week, that says, you figure it out, compiler. So what do you think? In this situation, could I use auto? Yeah, we can, because we're immediately assigning something to it. We're assigning numbers.begin. So numbers.begin is actually going to return an iterator of the right type. Basically, a vector of integers is the class I'm passing in, and I'm calling a function that returns an iterator. So the compiler can say, sure, this has to be a vector of integers iterator. So auto is fine here. And in fact, it's a very good use of auto, because this is kind of a long name. It doesn't really add anything. You could just say auto, and it is more succinct. Okay? There's a question of could I have used a type def to give it a shorter name? Yeah, you could do that too. So type defs are essentially just creating aliases for long type names. You could do that. But personally, I just use auto, because then the compiler will figure it out. Okay, so this is just talking about what I did. And we already talked about all of that. Okay, so I'm going to give you a little exercise now. So you've seen how iterators work. I want you to go through a vector, and you're going to write code to extract the negative values. Well, actually, we're not going to extract them yet. Sorry, let me change my words. Find the elements that are negative in this vector. So we're passing in a vector of integers. It's called integers. And we're going to make a vector of integers that's called negatives. And then we're going to return that. Okay, so I've already written the return statement for you, so that's fine. But you have to load up this negatives vector. And so every element in this integers vector that was passed in that is negative should be put into here, copied into there. And then you return a vector that has all the negatives. All right, so I'm going to create some breakout rooms, and you'll have a few minutes, about 4, to go off and try to do that in that online IDE. Okay, so we'll be back in about 4 minutes. Okay, welcome back, everybody. Let's see. How many of you were able to complete it in the time you were given? Just, or not. Just type yes or no so I get a sense of how the timing is. Okay, that looks pretty good. Okay, so let's walk through my version of this. So the code that I wrote, whoops, let's just mark that up a bit. It's reasonably similar to what I had before, at least for the declarations. So declare an iterator of the right type, call it IT, and set it equal to the beginning of the container. Whoops. let's see, and keep going as long as I'm not at the end, and increment through each time. Okay, so I'm just going to walk through the vector again. I check if the value is less than 0 by checking what I'm pointing at, dereferencing it, looking at the value. If it is less than 0, then I can use this handy pushback function to add it into my negatives vector. This is the default constructor of negatives. What's the size of it? So after this constructor, while creating this variable, what's the size of this vector initially? It's 0. Okay, so I think some people are putting in like capacity numbers, 3 or 1. You don't really care about capacity. That's an implementation detail by the authors of vector that makes it fast. So I showed that to you so you understand what's going on behind the scenes. Size is what you care about. And this default constructor sets size equal to 0. Okay, there's nothing in it. So it's an empty vector. I'm going to go through iterating through my integers vector. I've checked if every entry as I go through a loop, I check if that entry in the integers vector is negative. If it is, I insert it into my negatives vector where I'm building up my result. And so that's why I'm mentioning that it started with nothing in it. And I do that with this pushback function, which will add an element. And I don't want to add the iterator. It doesn't really make any sense. That wouldn't even compile. What I want to add is what the iterator points at. So the value that is there. Okay. There's a question. How does the iterator say the size is 0? Well, first the size of integers, which is what I'm iterating over here, is not 0. Okay, it's 4 in the example I gave you. But if the size of this was 0, let's say I passed in an empty vector, then what would happen is this iterator is set equal to the begin, and the begin. Well, so if my vector was empty. So let's say I have an integers vector. Whoops, let's try to spell integers correctly. So let's say I have an integers vector. And let's say it's empty. There's just nothing there. Okay, not even a single element. Then begin will point to the start of it, but the start of it, there's nothing there. So both begin and end will point at the same spot. And you will immediately fail this test. You won't go through the loop even once. You'd skip over the thing and negatives would return with a size of 0. Okay? So that's if I passed in an integers vector that was empty, had size 0. This code will work fine. Does that make sense? How will negative vectors have a size of 0? Because negative vectors is constructed when I create it. All C++ classes call some constructor. Because I didn't put anything in the brackets after this, I called the default constructor. I don't explicitly call it, but the compiler will call it to build negatives. And the default constructor for a vector creates a vector with size 0. Because that's the only thing that really makes sense. You say, okay, I made a vector, I haven't told you anything about it. The logical starting place then would be, okay, it's got nothing in it. Okay? Is pushback a typical constructor in a vector? So pushback is not a constructor, it's a member function. It is a common way to build up the data in a vector, but it's not called a constructor. Because remember, a constructor is a special function that gets called right when you declare the object. So you create the object, basically you declare the object and it's created when you hit that line of code by some constructor. So pushback's not a constructor, but it is a technique to get a vector built up bit by bit, and yeah, it is common. So, and I think Gonaker, you can ask more in the break, but I think you're mixing up capacity and size. So size is what you care about for a vector. Capacity is an internal, mostly something that is used for internal management of the vector for efficiency. You care about the size, which is how many elements have been put in it that you can access and work with. And the default constructor of a vector always sets the size to 0. Okay, there are other constructors that allow you to create a vector that has stuff in it already. I used one, let's see, I used one right here, right? So in this case, I created a vector and I immediately said it's got 4 things in it, so its size would be 4. And in fact, it would even have those values inside of it. So that's fine. But I didn't do that here. Here, I just said, create me a vector called negatives. And I didn't tell you to put anything in it. So the default constructor, the logical thing is it does what is logical. It creates a vector with nothing in it. Size is 0. Okay? Okay, so any questions on that? Any more questions on that? Or whoops. Hopefully it looks a little messier than indices, in my opinion. How many people like this code better than using indices? Because I could write this also with indices, like an integer and the square bracket operator. Okay. So do you like indices better, or do you like iterators better? And go back and I can show you the example where they're both on the same slide. Let's see. Yeah. So this example, they're both on the same slide. So there's going through a vector with indices, there's going through a vector with iterators. So one person likes iterators better. One now likes indices. Anybody else like indices or iterators? Yeah, most people like indices, and I do too. So the truth is, with vectors, I will usually write my code to use indices when I can. So if I'm just walking through a vector, I consider this easier to read as well, so that's usually what I'll do. They're both the same speed. Like, this will both work equally well. So there's not a right or wrong here, but most people would find the indices easier to read. But there are member functions that won't work with indices and container classes that don't work with indices, which is why we're learning to use iterators. But this doesn't mean, oh, I learned iterators, now I better stop using indices. If they work with the container class that you're using, go ahead, use them. They're fine. Okay, so now I'm going to do something a little more complicated. We built up that negatives vector, but we still have the negatives lying around in our original vector integers. Now I want to get rid of them. And that's slightly more involved. So I still declare an iterator, okay? Declare an iterator of the right type, vector of integers. I want the iterator to go with it, call it IT. I'm going to set it equal to the beginning of my vector, which is integers. And I want to keep going until I hit the end. So that all looks pretty normal. But there's something a little different here. This. I don't actually increment the iterator in the control of the for loop. So notice there is no increment there. In the body of the for loop, I basically say if what I'm pointing to is less than 0, then I want to erase it. Erase is a member function on containers like vector. So this is going to destroy whatever the iterator points at, because I want to get rid of it. It's a negative number, I want it gone. So it's actually going to destroy what's there, and it's going to fill in the hole. So the vector is going to get one shorter. Size is going to become one less, and a vector can't have holes in it. So it's actually going to shift everything over by 1. So if I just erased index 12, then everything after index 12 will be moved to the next lower index, and what was at index 12 is just gone. Okay, and then you notice that I actually update the iterator by setting it equal to whatever comes back from this member function. And I'll show you why in a second. I'm going to show you this with a picture. But basically, I just destroyed what the iterator is pointing at, so I need to update the iterator. It's pointing at something that doesn't exist anymore, and the way I do that is I actually capture the value that's returned from this member function. That was what I did if the number that I was pointing at was negative. If the number that I was pointing at was not negative, then I just skip over it, right? So I just increment the iterator, go to the next thing. So that's the easy part. Because I've done my manipulation of the iterator inside the body of the for loop right here, I don't increment it in the control, because that would be doing too much incrementing. And I'm doing more complicated updates to the iterator than just incrementing it. So I can't really do the control do that in the control part of the for loop, which is why I do it here. Okay, so this is just kind of saying that. So let me show you what's happening. And there is a good question. So Karniker's asking, well, wait a sec, what you described kind of sounds slow. Like, this is moving all the numbers going to be slow. And yeah, it is slow actually. For a big vector, it's a slow operation. Okay, so let's look at what erase does. So this iterator starts at the beginning. That's what I wrote. And it's gradually walking through my integers vector. Let's say I'm pointing right here. This is where my iterator is. and it's pointing at a number that happens to be negative. So let's say it's -5. So I'm supposed to get rid of that. So I call erase, and I pass in the iterator. So I say destroy what is there, and so this is an integer, so destroying it is trivial, but if it was a class, it'll call the destructor of that object. And after that's happened, it shifts everything after this over by 1. Okay? And that can be a lot of work. If this went to 100,000, now it goes up to 99,999, right? One less index, the size is one smaller. That involves a lot of copying. So it's actually going in, you don't call this, it's all happening inside vectors. So from your point of view, you just wrote this one line of code, but the vector actually will have a loop. The actual vector class has a loop in it that walks through and copies every element over by 1 index, which if there are a lot of elements can be pretty slow. And then it returns an iterator to the next element, the one that was over by 1. And it needs to do that because you just destroyed something. So what we were pointing at is no longer valid. We basically update the iterator. Does it make sense? Okay, I don't see any questions, so I'm going to take that as, yeah, you got the idea. This is just fundamental, so it is slow, but this is fundamental to a vector. A vector cannot have holes in it. That is the definition of a data structure. It works like an array. That's what actually allows us to do this nice random accessing, is we can't have any holes in the vector. That means if we erase something in the middle, there is a lot of copying to get rid of the hole that we just created. So there's a question, what if we erase the last element of the vector? So that one. So we had an iterator that's pointing at that, and we call erase. Well, actually, it's the wrong function. Sorry, I should write, it would be something like vec.erase of the iterator pointing at that. It's fine, and in that case, there is no copying. So the vector would say, how much do I have to copy? Nothing to copy. So I just destroy that, and size becomes 1 less. That particular case would be fast. Okay, so how slow erase is depends on where you are in the vector. The closer you are to the front, the slower it is. But on average, it's going to be slow. Okay, and then what erase returns is an iterator. So it's something of, in this case, we're using vectors, so it'll be an iterator to a vector. It returns just basically the iterator, the pointer to the element that was right after what you destroyed. Okay, and that's so that you can keep working if you're walking through in a loop. So it doesn't return, oh, and you're saying what does it return in that case? In that case, it would return end. Yeah, so Mark's right. If you were pointing at the last element and you called erase, then what would be returned as the new iterator would be end, so that you break out of the loop if you're using a loop. Okay, so how does erase perform? So we already talked about what it does. The complexity is order n. It's order n because it has to copy up to n elements. And on average, if you call erase on random spots in the vector, in the average case, it's going to copy n over 2, which is still order n complexity. So that's slow. Okay, so given this, let's go back to our remove negatives function and see how fast is that? Okay, so let's go back to it and look at its computational complexity. So here's my remove negatives function. And the worst case is going to be if I had a vector that's all negatives. What's the order of this? So order 1, order log n, order n squared, order n cubed. Okay, so I see an n, I see an n squared. Any other votes for anything? N squared, yeah, so we've got a couple of n squareds. Okay, so yeah, it is n squared. Basically, this erase function we just saw is order n, and then we can walk through, we'll walk through this loop n times, 1 for every element in the vector. So we're going to go through, and n times we're going to do something that is order n. So together that is order n squared. Okay, which sounds kind of slow, and can be slow. Okay, so, well, I kind of gave it away, but what do you think we can do to make this faster? how would you speed this up? And if you can read fast, you already have a hint. So just type in what you would change in order to make this faster. Because n squared is bad if n can get big. So you really want to avoid it if you possibly can. And what we're doing doesn't seem that complicated. It seems like it should be possible to do it faster. So what do you think? Okay, so Simon just wants to change the spec, right? Like learn to live with negatives. Sometimes you can do that, sometimes you can't. Yeah, so Jezreel's right. So use a linked list. That's going to be a lot better. Okay, so, and the STL has a linked list. So we've talked about vector a bunch. There's another class called standard list. It's a doubly linked list. It's just like what you built in ECE 244. Basically, every node in the node has a head. The class has a head pointer, a tail pointer to the start and end of the list. Every node in the list has some data. That data is templated, so that's whatever you want. And then it has a next pointer and a previous pointer, just like you used in 244. You don't really see these next pointer or previous pointers. Those are hidden inside the class, so I'm showing you how it works, but you don't really need to think about this too much. So the nice thing about a linked list is that you can quickly erase things and you can quickly insert things. So let's say I wanted to erase this. So I have an iterator pointing at there, okay, and I call erase on it. What do I need to do? Well, the destructor of this object is called, so we get rid of that memory. We don't really do this. The list class will do it for us, but the list class will update that next pointer to point there. It'll update this previous pointer to point there, and that's it. So, and that's fast, right? That is order 1. Same thing for insert. If I wanted to insert a new node, the new node would be created. Okay, so it'd be constructed, and basically I just got some pointers to fix up. So I would take this next node and make it point there, and I take this one and point there, and do the same thing for the previous. So insert and erase at arbitrary points in the list are order 1, as long as you have an iterator to where you want to put it already. Does that make sense? Okay, so this is kind of the key thing you do with the container classes in STL. You think about what container for this data makes sense given what I'm going to be doing. So right now you know 2 containers, list, well, vector, and now you know list. So what can you do with them? Well, you can ask for an iterator to their start. So you can do that on both of them, and that's fast. It's order 1. You can check if you're at the end using, again, an iterator, and that's also fast. You can do pushback to grow the list or the vector from the end. It's fast. A vector knows its size. A list actually knows its size as well in the recent versions of the standard library. The way it knows its size is they decided this was common enough that they just basically made a private member variable called size. So they stored a little bit of extra information. So now they can answer the question, how big am I, in order 1 time. Okay, so that's also fast. Square bracket operators, the indexing operator. It's fast for a vector because it works just like an array. It is not available for a list. It will not compile. The reason it's not available is it doesn't really make sense. You don't have random access to this data structure. If you ask for the 50,000th element, you can't get it in any efficient way. The only way you could get it is actually to start at the head and walk through the whole list until you've gone through 50,000 nodes, which would be really slow. Doesn't really make sense. So the creators of STL basically say, that makes no sense. Do not use that. We will not build that. So it just won't compile. And that's a good design decision. They're actually doing you a favor by code that would be really slow because you're using inappropriate data classes. Just doesn't compile. So it helps you find that doesn't make any sense. Don't do that. Much faster. Okay. Erase is, we just saw it slow. For vector, insert is the opposite of erase. Given an iterator, you can put something at an arbitrary point in a vector or a list. And it's also slow for a vector for the same reason. You got to shift everybody out of the way to make a hole in the vector, and then you put the new thing in. For a list, those are both fast, because we just saw that it's all local operations for a list. So each of these has a reason to exist. If you need random access, if that's useful in your program, you should be using a vector. If you need to be inserting or erasing and inserting at arbitrary points, then you should be using a list because it's going to be much faster. The iterators, there are different groups of iterators in C++. So the most powerful kind of iterator, the most flexible, the most feature-rich is called a random access iterator. So that's the kind of iterator that a vector gives you. It allows you to increment the iterator, it allows you to decrement it, and it also allows you to just skip forward an arbitrary number. You can do things like take the iterator plus 5, take the iterator minus 3. So you can jump around with the iterator, essentially doing random access like you would with an index. The iterator for a list is of a group called bidirectional, which is a little weaker. It allows you to increment to go to the next element, decrement to go to the previous element, and the reason is both of those are fast. We just look at inside the list class, it just looks at the next or the previous pointer. It can do this quickly. It does not allow random access. You can't do things like IT plus 5. Doesn't make sense for a list because the only implementation of that would be very slow. They don't want you to use it, so it won't compile if you try to do that. So see, there's a question. What's the point of using an iterator list? Wouldn't you use the header tail pointer? You can't access the header tail pointer. Okay, so that would be a really bad class design if they expose the head and tail pointer because they're exposing implementation details. The idea of a class like list is the head and tail and the next and previous. This is all hidden from you. It's all inside the class, but you don't see it. You make calls to do things, and the fact that those use the head and tail pointer is hidden from you. That makes your code simpler, more readable, allows the library developers to optimize and change the list without you being affected. It also allows you to use consistent naming. So notice that to get a pointer to the start, well, to write a for loop that goes through a container class, you can do it with just begin and end. Okay, and you can do that regardless of whether it's a vector or a list. So that's on purpose. If they exposed head and tail and so on, you're devolving back into just writing your own lists. So you don't want to do things like that. So let's just summarize those iterator categories. So random access, which is what a vector gives you, and a few other classes. Most powerful, supports all of these operations. So all the ones I talked about plus dereference, so get the value it points to. Bidirectional, you lose that random access, the ability to just change an iterator by adding 5 to it, for example. There's a weaker class still called forward iterators. Forward iterators are used with things like forward list. Forward list is a singly linked list. So basically it's another class in STL, and it has next pointers, but it doesn't have any previous pointers. Okay, and what that means is it saves memory, so it's a little bit less memory, but it means you can only go forward. You can go to the next element, but you can never go to the previous. So that means they can't implement the decrement in iterator, so this class doesn't expose it. Okay? Hopefully that all makes sense. If you try to do something with a certain kind of iterator that it doesn't support, you'll just get a compile error. So you go, oh, it doesn't support that. I should maybe use a different container class or not use that operation. Okay, so let's look at what we have to do in our remove negative function that we just wrote. How do we change it to use a standard list? So this is what we had with vectors, but it's slow. It's order n squared. So just type in the chat. What do we need to do to make this work with standard list? So take a shot at it. Yeah, change vector to list. So a couple of people have jumped in with, and it's just that easy. Okay, so you literally just change the word vector to list in the places where we declared integer and where we declared the iterator, and everything else works the same. And it works the same because we have the same member function names. We're using begin, we're using end, we're using dereference operators. Those work the same for all of these iterators. So nothing happens. We don't have to change anything else. The code that gets generated by the compiler is different, but we didn't have to change anything else. So that gets back to the question about should the list expose head and tail and so on, this iterator abstraction has allowed us to switch from a vector to a list without rewriting any code. So this is showing the power of the abstraction, that we really can reuse our code in a better way without worrying too much about the underlying details of how it was implemented, how these container classes were implemented. Let's see. With a list, basically this erase becomes order 1, and we're going to go through this n times. So this becomes an order n operation instead of order n squared. Now, if our original function had used some iterator capabilities like random access that didn't exist with with lists, or we use the square bracket operator with our vector, okay, then changing to a list wouldn't compile. So yeah, if you use some features of a container that another container doesn't have, or features of an iterator that another iterator doesn't have, then just changing the name, you'll have to do more work. But if you're only using things that both support, you can just change the name of the container, it'll be fine. Okay, so this came up earlier. Basically, these types are a bit long sometimes, so we can use the auto keyword to simplify it, and you can use it when the compiler can figure out the type. So it's when the variable, the object that you're creating, is immediately being assigned something. That's when you can use the auto keyword. You should still know what the type is. It should not be mysterious to you, like, what is this thing? And the type is still static, so it doesn't change at runtime as you go through this function multiple times. So in Python, that can actually happen. Python is what's called a dynamically typed language, which means variables can change their type as the program's running. In C++, that doesn't happen. It's called a statically typed language, where you have to say what the type of everything is. And that's done so the compiler can do more checking, and so your code can be faster. So it makes a little more work for you, but it suits the use case of C++, which is fast code in large systems well. Okay, so if we want to use the auto keyword, kind of already talked about this, but it's pretty simple. We had this long declaration here, and we just changed that to auto, and it works because we're immediately assigning a value to this iterator, so the compiler can figure out, based on this function that we're calling, what the type is, and it just pastes it in. So it's like you typed it. Okay, so I'm going to pause there while I get a VNC machine going, and we'll come back in 5 minutes. So I'll start at 11:15 a.m. or maybe 11:16 a.m. Okay, so we're back. So I want to do a quick demo before we go into the next set of slides. So, whoops. Okay, so this is the code that we basically just wrote. So I've got a main function here that defines creates a vector that has 1,000,000 elements in it. So this vector v0 is created by this constructor of size n is 1,000,000. So it's got 1,000,000 elements, and then this loop here goes through and populates the vector by writing random data into it. So it writes random data into every element of the vector, and the data is half negative and half positive. So it's between negative 500,000 and positive 500,000. And then we go through and we remove all the negative numbers. And we do it the way that we just wrote. So we start at the beginning of the vector until we get to the end of the vector. We go through, and if that element is negative, we erase it. And if it's not, we just skip over it. Okay, and we said that this was order n squared. So I want to see how fast this is. And let's see, let me keep that up there on the screen. And here's another version of that. Okay, so here's another version of that function. And all of the code is identical. The only thing that has changed is on the left, I've got a vector. And on the right, I've got a list. So we just changed the type from vector to list. Everything else is the same. And we said that list is order n. So Okay, so we expect order n to be faster, obviously, than order n squared. How much faster? So I'm going to make the programs so we can see. I should always do speed tests with the release configuration. So I can build in NetBeans. I'm just doing it at the command line. But the build I want is release. So I say make configuration equals release. Okay, I haven't changed any source files, so I just say clean up. You can use the up arrows to go back to old commands. So I say run that build again. Okay, so I built both of those programs, and you can see this -03 means the compiler is optimizing the code. And 03 means highest optimization level. Optimize it for speed as much as you can. Okay, so now I can time this. So let's do the vector one. How much faster do you think list will be than vector? Yes, we'll start the vector running and type in the chat. You know, you think it's twice as fast? You think 3 times as fast? 10 times as fast? So we got 1,000,000 elements in our vector, half negative, half positive, and we're using an order n squared algorithm with vector, order n with list. What do you think? Take a shot in the chat. Okay, so 500,000 times faster, 2 times faster. So a large range, right? So we've got it's like Price is Right. So how fast do you think it'll be without going over? All right, so vector's done. So this time command prints out a few different things. This is the key number that I care about. It says 34 seconds, 34.58 seconds. So that's how long it took. So now I'm going to time my list version. Okay, so time list erase, and it took 0.17 seconds. Okay, so from about 35 seconds down to 0.17. So that's about maybe what's 5 times 35? I guess 400 times. For this particular case, it was about 400 times faster, which is kind of halfway between what Simon and Jasnewer said. So it's a big difference. So the reason I showed you this is when you're doing your project, you need to make certain functions fast. We actually speed test them. Also, just your program will be really slow if you code it with the wrong data structures. You can't speed your program up that much by micro-optimizing the code. You know, you can speed it up some, but if you've used an order n squared algorithm or a data structure that makes your algorithm n squared instead of n, you cannot fix that by going in and trying to just micro-optimize the code. You know, get rid of a few statements here and there. You got to get the data structures and the algorithm right first. And in this course, we don't really care too much about micro-optimizing the code, so we're not going to have speed tests so tight that you ever have to do that. But you do have to think about the complexity of what you're doing, so that you don't use a really slow data structure for the purposes that you're trying to achieve. Okay, so let me go on to some additional STL containers. Okay, so now we're going to talk about some more containers. So you've seen vector, you've seen list. We're going to talk about a different group of containers called associative containers. Vector and list are called sequential containers. It means they have an ordering. There's stuff in index 0, 1, 2, 3 in a vector, and in a list you can iterate through and things come out in the order you put them in the list. So those are called sequential containers. An associative container works a bit differently. And I guess I'll show you what that is in a minute. So what are they? Why would you use them? Okay, so let's say you want to find a value in standard vector. So I'm not asking what's an index 2. In a vector, you can get that really fast. I'm instead asking, go find me, is the name, say I've got a vector of strings, does the name Vaughn occur in this vector? Okay, so in order to do that, I have to look through the whole vector. So let's say I've got a vector of strings, and let's say I'm not looking for Vaughn, let's say I'm looking for the string law, okay? I can write a for loop to do this. There is a templated function inside of the standard library, so I'm just using that. So this is part of STL as well. So I can call this function called find. It takes 2 iterators, so a begin and an end iterator. So I'm saying I want to search my whole vector. So from the beginning to the end, I want to search for this string la. And maybe this is my vector. Okay, so I've passed in these two iterators. This function will search everything between those iterators, and it's going to find that, yeah, there's a match, and it's going to return an iterator to that match. So that'll be my found it. Okay, so I can do this without much code. That was actually nice. I made one function call, and I could find, does this value exist in my vector? But it has order n complexity, because it has to go through every element in the vector, or at least until it finds one, because it returns the first one it finds, but it has to go through and check every single element. Is it the right value, or the right string? Now, I could do better than this. You learned in 105 and 244 that there are more efficient ways to search. So I could sort this vector. Let's say I'm going to do many searches. If I was just going to do one search, then I should probably just do this. It's fine. But let's say I'm going to do many searches. That's a big part of my program. Well, then I can make this a lot faster by sorting the container and then doing a binary search. But you could code all that, but it's going to be a pain. If you're going to put new data into the vector, you've got to resort it. It's easy to forget to do that. You have to write more code. It's easy to have bugs. So doable, but it's not the best solution. Okay? And I see there's a question, is foundit an iterator? Yeah, foundit is an iterator. So standard find returns an iterator. So basically a pointer to the element that it found. Okay, so I'd rather not put this in a vector and sort the vector, because it's going to be error prone for me to do that. So what can I do instead? Is there a data structure that would be more appropriate if basically this is a key thing I want to do? I want to go look up elements, look up strings in a vector. Is there something else I could do? Yeah, so binary search tree would work. I also see people saying hash table. That would also work. So yeah, both of those are much better choices than putting this in a vector for what I'm trying to do here. Because basically I'm not trying to access it by index. Accessing by index is what vectors are really good at. I'm trying to do searches by what would be called a key, what I've stuck in there. So a binary search tree would be good. A hash map would also be good. I'm going to go through a binary search tree first, and then we'll talk about hash maps after. Turns out in STL, the way you work with them is very, very similar. So once you understand how to work with one of these, you pretty much know how to use the other one. Okay, so what we're going to do is we're going to use a binary search tree, because that's a better solution. And STL has a binary search tree in it. It gives it the name map. Okay, so what is map? It is a self-balancing binary search tree. Do you guys know what this means? What does self-balancing means? Balancing mean? So what's a balanced binary search tree versus an unbalanced one? You should have learned this in 244. Okay, so people are saying yes, yeah. So basically a balanced binary search tree has the minimum number of levels. Okay, so if I have, I don't know, 1, 2, 3, or 6 nodes in a binary search tree, this would be considered balanced because it's got the minimum number of levels. It looks like a tree. A very unbalanced tree could look like this. All right, not a very good binary search tree. It's legal, but it's not very fast, because to search this, you have to basically do a comparison at every level to do searches in a binary search tree. And this has more levels, it's going to be slower. For 6 nodes, it's not too bad, but if I do this for 1 million, it's going to be bad. The binary search trees that you learned, that you studied in class in 244, didn't balance themselves. You basically inserted things wherever it seemed like it was appropriate, and you erased them from wherever they were. The binary search trees inside the STL library are a bit more fancy. What they do when you do an insert or an erase is they check those member functions without you doing anything. They check, is the tree getting too unbalanced? So is it getting too much like this? And if it is getting too much like that, they basically restructure it to make it look like this again, okay, to keep the searches fast. You don't do anything, this is all happening behind the scenes, but what it means is that it is guaranteed to be login, okay, for find, insert, and erase, because the tree is guaranteed to be kept at least close to balanced, okay? So it's better than, even if you went and code your own binary search tree, you have to code a pretty fancy one before you're going to equal what you get for free by just calling the STL. Standard map uses standard pair as a key part of it. So remember, we coded standard pair, or we coded the pair templated class last week. There is a pair inside the STL, so you don't really need to code your own. You shouldn't code your own. You should just use this one. But remember that it's got two data members, and that's all a pair is. It's just two pieces of data that are grouped together. Pair, we're going to use with a binary search tree as the first element is the key, so the way we want to look things up, and the second element is the value. The value is like just data that comes along for the ride. So, and every node in the binary search tree, so I drew out what was the binary search tree. This node has two things in it. It has the key and it has the value. And they're in a pair. Okay, so that is what is at every node. So let me give you an example of how you can use this. So a domain name lookup is a key operation in the internet. So you connect to the UG machines by typing names like this. You say, I want to SSH to ug152.eecg and so on. So that's what you'd like to type. It's easier to remember. That's not how the internet works. The internet has to send packets to a specific IP address. IP addresses are, well, I'm doing 32-bit IP here, so they're 32-bit integers. So it would be a number like this. That number represents where should you send packets if you're trying to talk to this machine. Usually when you are shown IP addresses, they show them 1 byte at a time. So it wouldn't show you this big integer. It would instead show you the first byte is this, second byte is that, third byte is that, fourth byte is that. That all is actually an integer. It's just written out in a nice format for you. A domain name server takes a string that represents some computer and it returns the IP address. So an integer that is actually what you can connect to. And you want it to be fast, right? There are a lot of computers on the internet, so you're going to have a lot of different strings you could query. You're going to have a lot of people asking questions at once. You want this to be quick. So we're going to do it in a binary search tree. So the key is going to be a string. That's the name of the computer or the domain. The value is going to be an integer, which is the IP address. So we're going to make a binary search tree, and binary search trees in STL always take a pair. So the pair is going to be the key, which is a string, and the value, which is an integer. Okay, so hopefully everybody's with me. Type in the chat if you're not. Okay, so how does this work? Well, we need to basically first get access to the functions, and the class. So we include map. That's where the code lives for this binary search tree in STL. So I'm inside my main function. First thing I need to do is I got to declare the binary search tree. So I'm going to call it DNS lookup. So that's the name of my map. And I'm asking for a standard map, and I need to say what the key is. So the key type is going to be a string, because I want to look up by name. And the value, the data that I would like to come along for the ride, is the IP address associated with that string, so that's an integer. Okay, so this has created a binary search tree for me. It's initially empty. I didn't specify anything in the constructor, so I get an empty binary search tree. I'm now going to start putting some data in the binary search tree. So let's look at how we do that. There are a few different ways I could write this, so I'm just going to show you 3 ways I could write it. First one's kind of the most explicit. So I say I'm going to put something in a binary search tree. What I put in a binary search tree is actually a pair. So it's the key, which is a string, and the value, which in this case is an integer. So I need to make a pair of data. And my object I'm naming Google. And I want the constructor to initialize it with this string and this integer. So I'm going to get a pair that has Google as a string, and then this particular integer is the IP address. And then I just insert that object. So there's a member function called insert. We just talked about it for vector, but basically there's a member function called insert that puts new elements into a binary search tree. So I just pass that pair object in, and it'll be put in the tree. Okay, next option is just a little bit less typing. So I'm going to use the auto keyword. So I use the auto keyword so I don't have to type all this, what kind of variable should I have. And I use this templated function that the standard library gives me called make pair. And I just say with this string and this integer, make me a pair out of those. It'll figure out the right types and make me a pair. And then I say assign that to this Apple object, and you figure out the type for it too. Okay, so this will all work, and all the types are just figured out and work. And then the last thing I can do is if I want to do this in a more succinct way still, I don't really need this object. I'm just using it as a kind of a variable that I pass in here. So I can just basically directly say, take this string, this integer, make a pair out of them, and insert that in the binary search tree. So this one is kind of the shortest. It's what I'm going to use on the other slides. But just so you understand, you can write it in a kind of longer, more explicit way if you want. Okay, let me erase all this stuff. This just basically says what I talked about. Okay. And let's see, could you do standard pair Apple equals, I don't think, so actually has a question about could you do essentially an aggregate initialization. I think that particular syntax that you're writing there will not compile, actually. But the best way to do it is to try it in a C++ compiler. In this course, it's more like what you would do in your career. We're not going to ask you questions. Your TA is not going to ask you questions of would this compile, would that compile. I'm telling you what works and what doesn't, so you have some understanding of what you can do. You actually type it in the compiler and see if it compiles. And if it doesn't, you go look up why. Oh, I meant to do this. Why does it not quite work? Oh, I got to change the syntax a bit. Does that make sense? So I don't think that exact one is going to work, but I use a compiler, frankly, to check complicated syntax questions. Okay, so now I'm just using the short form of how I build up my binary search tree. So I've declared my binary search tree. I'm inserting 3 things in it: Google, Apple, and University of Toronto with their IP addresses. And now I want to actually go and look up names. So I'm using auto again. So I'm saying I'm going to make an iterator. Find returns an iterator. It searches an object. Whoops, this got lost. I'm not sure why that's not showing up. But it searches an object. So I say on my binary search tree called domain name DNS lookup, call the find function, and that's going to return an iterator. So a pointer to some node in the tree. What should I pass to find? And let me do a quick poll on this. Okay, this is again kind of just for understanding. Try to guess what would make sense to pass into the find function. All right, so I'll just give you, I don't know, 30 or 40 seconds to just take a shot at this. And you think about, what are we trying to do with a binary search tree? So what makes sense to pass into find? What it returns is an iterator pointing to the node in the binary search tree that matches, but what should we be asking it? Okay, so I'm just going to give you a few more seconds. So Armin, I see you have a question on how does the tree balance. How about I answer that after class, because it's a little bit more involved, so I can give you some pointers on how it's done. Okay, so last, I don't know, I'm going to give you 5, 4, 3, 2, 1. So take your last shot, and let's see what people said. Okay, share the results. Okay, so 56% of you said that it's a key is what we should use to look it up. 27% said a value, and 18% said a pair of key and value. Okay, so let's start, and nobody said the number 5. So yeah, the number 5 would be really easy if you just said, you just always pass 5 and it does the right thing, but that would be magic, so you all excluded that. Let's say it returned a key and a value. So a key, or you passed in a key and a value. That's basically everything that's at a node in the binary search tree. So if you already knew the key and the value, it's not quite clear why you need to do a find operation, because you already have everything you need. if you pass, and so between value and key, the binary search tree is sorted on key. That's what you can efficiently look up. The value's coming along for the ride. So there's no way to search a binary search tree efficiently by value. It's the key that you're sorting on. That's what you pass into the find function. Okay, so yeah, so most of you guessed that, and if you didn't, that's the answer. Okay, so we pass in the key. So let's say one of our keys that we're looking for is Apple. Okay, so we can pass in that string. It's going to return an iterator, so a pointer to the node that matches this key. How do you think we should check if the key was found? So this is again guessing what makes sense, right? There's documentation on the web, so if you couldn't guess this, you would just go look it up, but it's useful to just think, can you guess what makes sense? Okay, so it's going to return an iterator, but how do we check? We need some way to say that we didn't find it. Okay, so if we have an iterator, and if we found it, the iterator is going to point at that node. Yeah, and I see people you return the end iterator. That's exactly the right answer. So if it was found, the iterator will not be equal to this end value. So you can think of this end value. Remember, it doesn't represent any valid point in the container. You can think of it like a null pointer. So in a vector, you can think of it as being just past the end of the vector. You can also think of it as being an equivalent of a null pointer. It means that this iterator is not valid. You can't use it. So we can check if the iterator is not equal to this end value. Well, then it's valid. And if it's valid, remember the iterator points at an entire node, okay, in the binary search tree. And then the node in the binary search tree stores both the key, which in this case was a string, and the value. Okay, so it's pointing at a pair. So if we want to print out the key, we actually say print out the first element in the pair. If we want to print out the value, we say print out the second element in the pair. So that's what we're doing here. So we have an iterator, it points at a pair, point out the first thing, which is a key, point out the second thing, which is the value. Does everybody remember what this arrow notation means? What does that mean with pointers? Yeah, so I choose right. So it's member access. So if I have a pointer to a structure or a class, I can use this arrow to basically say I'm accessing this member of the class. And if you have the object, you use dot. If you have a pointer to the object, you use the arrow. So that's what this is doing. So this is going to print out, well, I believe I showed what it'll print out. Okay. So yeah, it's going to print out apple.com, which is the key, and it's going to print out this IP address. And let's see. Let's say we ask for Microsoft. Microsoft is not in the tree. I didn't put it in there. So this is not going to be found. It's going to return an iterator, and that iterator will actually match the end iterator. So, and that's again our flag value, our sentinel, that says I didn't find it. Okay. So we do these special checks of are you equal to the end iterator to check are you valid or not valid. Okay, and hopefully that answers your question, Abby. If not, maybe ask me more after class. Okay, so we print out couldn't find it. Okay, let's iterate over a standard map. So I've made the same binary search tree and put things in it. And this kind of shows you also why you use iterators. So with a vector, we could use indices. But we saw with a list, we couldn't. And we also can't iterate over a map with indices. Doesn't make any sense. We, again, need to use iterators. Okay, so I'm going to put you in breakout rooms and take a shot at coding this over the next 4 minutes or so. So let me quickly put you in. Okay, welcome back, everybody. I guess same question I always ask. How many people were able to complete that in the time? So just type yes or no, depending on whether that was a very short 4 minutes. Okay, so I thought I went all the way to 4 minutes. Maybe I cut one off. Anybody else able to complete it or not complete it? Okay, it's a bit short. Okay, I'll try to remember that for next time. I'll pass it on to Andrew. Okay, so let's look at how we iterate over it. So the code's actually not very long. So we just basically use our begin. Okay, so we declare an iterator. We're going to use the auto keyword again because that's convenient. These iterators start looking pretty complicated looking if you don't use auto, so it's nice. We set it to point at the beginning, and we keep iterating as long as we're not at the end or past the end, and we increment the iterator. And for every node, we want to print both the key and value, so we're going to say print out the first member of the pair, which is the key, print out the second member of the pair, which is the value. So the code's actually quite short. Okay, and it'll print out that. Now we inserted this in the binary search tree. You know, we put in Google, then we put in Apple, then we put in Toronto. When you print it out, it'll actually come out in this order: Apple, then Google, then Toronto. Why do you think that is? What do you think has happened here?
Make sure it's muted.
Pushback. No, I never called pushback. So yeah. So remember, it's a sorting data structure. So we're sorting on the key. The default comparison for strings, which is what we're going to use, the operator less than is what the map is going to use to sort, is just going to put things in alphabetical order. So that's the way the tree is stored. When we do this traversal, this is an in-order traversal. Comes out in the sorted order. So that's, again, in an associative container like this, the order that you put things in is not the order they come out in if you iterate over them. If that's important, then you use a vector or a list which maintain the sequence in which you put things in. These containers do not. They instead are optimized for storing and looking things up by key. Okay, so let's say we had duplicate keys, because this happens sometimes. So let's say I'm not going to do a domain name server anymore. Now I'm making a salary database. So I'm going to still use a string as my key. It's going to be the name of the employee, but now I'm going to have a floating point value, which is the person's salary. And I'll call my object salary database. So I'm going to insert some data in it. So John Smith makes $45,000 a year, Mary makes $90,000, and so on. But even though my company only has 4 people, and it turns out we got 2 John Smiths. Okay, so there's another John Smith that makes $30,000 a year. What do you think happens? So I basically insert all these things, and then I say I want to find the entry for John Smith. Okay, so I'll get an iterator to that, and I want to print out the key, print out the value. Okay, so I'm going to print out, key is going to be person's name, value is going to be the salary. What do you think this code's going to do? What's going to get printed out here? I have 2 John Smiths. What's going to happen? Prints out the second one? Yeah, so that's a good guess. Actually prints out the first one. So with a key, it will not insert duplicate, or with a map, it will not insert duplicate keys. So all of these 3 entries go in my map. This one is just ignored. Okay, it won't happen. So when I go to print this out, I'm going to get John Smith earns $45,000. And in some cases, this is fine. This may be exactly what you want. You do not want to put any duplicates in, then a map's perfect for you. But in this case, I actually would like the duplicates. I'd like to know about both of these people. So there's actually something called a multi-map. So there's another class in the STL, works just like a map, but it's called a multi-map. And let's see, I think this actually might be, I'm just going to quickly flip through and see if I've got the latest slides. So I'm actually one entry behind on slides. Let me discard this and see if I can reopen this. Okay, so let's reopen this file and see if I can get the latest version. Sorry about that. And let's see. looks like it's not going to be super easy for me to do that. So I think I'm just going to leave it alone. Okay. So we have another kind of structure in the STL called a multimap. And it's just like a map, but it allows you to store multiple entries with the same key. Okay, so we can have multiple values associated with the key. So we can put John Smith in twice. Okay, and let's see. Let me go back to this one. So all I've done here is I've changed from a map to a multi-map because it turns out I want to store both John Smiths. That's better. They both go in. But if I ask find to find me the entry for John Smith, find returns a single iterator. So it cannot return me, both of these nodes. These are two different nodes in the binary search tree. So it's going to arbitrarily pick one. So I'm going to get one of these two. I don't know which one. So it hasn't really solved my problem. So you're going to find that the STL is very powerful. It has lots and lots of features. So let me see if I can bring up a web browser here quickly. And let's see. Okay, so you won't remember everything about the STL. Nobody does. But there are references, and I have links to these at the end of the lecture. One of the ones that I like a lot is called c++.com. So you go there and you go, okay, I'm not quite sure what to do. I almost have a binary search tree that does what I want, but this duplicate key thing is getting me. So I'll type map, because I know that I want a binary search tree. And if I look down here, and this is basically showing me classes related to map. And you see there's a map, which we've been using. And it says, well, there's a map. Oops, it does this annoying thing now where it shows a few advertising pieces, but it's still a good website overall. There's a map and there's a multi-map. Okay, so if I read this, I could actually figure out, well, the difference between these is what they do with duplicate keys. So I want a multi-map. So now I've clicked on multi-map, and I read the first little bit of information about this. And it says, okay, so it gives me a bunch of information about it. I'm kind of having a problem with the find function. So the find function is returning one element, and I really would like to get more than one. So this tells me how the find function works, that it returns, and you pass in a key, and it returns an iterator. And then it also tells me something pretty useful. It says, notice that it returns an iterator to a single element, even though there might be multiple elements with the same key. If I want the entire range of equivalent elements, then I should probably be looking at this member function. Okay, and I can either click on that link, or I can look down here and see what are the member functions. So there are a bunch that we've already been using, begin and end and so on. In erase, there's find, and it just told me to go look at equal range. So there was a link there, but I'll click here. If I click on equal range, it says it returns a range, the bounds of a range that include all the elements that match this key. So this is the kind of thing that you'll do when you're trying to figure out, is there a way to do this with STL? Something that you think should be doable, but you're not quite sure. So I've figured out this equal range function seems promising. So now we go back to the slides now. And I went through that pretty fast. So if you're going, wait, I can't read that fast, that's fine. I'm just trying to show you how to search the documentation. But you obviously would read it more slowly than that. But I've now got this idea that equal range is going to help me. Okay? And if I read that documentation carefully, it says equal range will return a pair of iterators, where the first one is the beginning of a range, and the second one is the end. And iterators in C++, you always should stop before the end. The end is considered just past what you want. And it's going to give us the range of entries that match the key John Smith. Okay, so this is the code I would write now to print out all of the John Smiths. Instead of calling find, I'm calling equal range, still pass it a key. The type of this is kind of messy to write, so I'm just going to use auto. Okay, this is actually returning a pair of iterators. I start, so I can loop through them. So I can loop from the start of the range, so range.first. I can go through the range, but should not ever look at the last thing. C++, the STL always uses this convention of begin exists and end is just past where you want. And then for each one of these spots, each one of these nodes, I can print out, my iterator is now pointing at a node. I can print out the key, I can print out the value. So this is going to walk through the whole range of nodes that match John Smith, and it's going to print out this. Okay? What it actually looks like, if I can quickly insert a slide, because this might seem kind of abstract. Okay, so let me just put this slide in and draw on it. I have a binary search tree. Okay, and this was like Mary. This was John. This was another John, and I think I had a Gary. Okay, so that would be a binary search tree. It's actually sorted. This equal range is going to return a pair of iterators. First iterator is going to be there. Okay, so that's going to be the first one. And the second one is going to be there. And that indicates the end of the range. When you iterate through a binary search tree, the iterator is bouncing around the tree. The class understands how to do that. So this is where you would iterate, this is where you would look at first. Then when you increment the iterator, it will actually point at this node. Okay, so your iterator will now point there. Then you increment it again, it'll point at this node. And you would check that node is the end, and you would stop. You'd stop the iteration. In a binary search tree, all of the, it's sorted, so everything that matches John would be in the same part of the binary search tree, if that makes sense. So it's a little more abstract than just looking at a vector, but remember that you can iterate through a binary search tree by basically adjusting what this iterator points at. Hopefully that made some sense. If not, hang around afterwards and ask me a question. Yeah, if you look at this code, so there's a good question. Does it print out the second one? You notice that I say it not equal to range.second. So we stop when we hit the second element. So when we're pointing at the second element, which would be Mary in my case, it's not a John Smith, we don't print it out. That told us to stop the loop. Okay, so that's our sentinel value, kind of like end always is. Okay, so other containers. Again, this is just to point you towards the documentation. So we talked about map. It's a binary search tree, so find, insert, and erase are all fast, log n. Multi-map is just another form of binary search tree where you can have duplicate keys. Also log n for find, insert, and erase. Unordered map is a hash table. It's a little faster. It's order 1. It's not sorted, so you use it when you don't care about sorting. If you cared about sorting, then don't use it. Like if you need to traverse it and get the keys to come out in the right order, don't use it. Otherwise, it's a bit faster. And there's something called a standard set. Standard set is just when you don't have values. It's a binary search tree where the key is all you need, which happens sometimes. In that case, the set says, okay, you don't need to give me any values. I'm not going to talk about these, but there are a few other containers that are just variations on a theme. They're not as important. Few words, I know I'm over time, so feel free to sign off if you have to go. These will be recorded too, but we'll be done in the next few minutes. Okay, map versus unordered map. So the way you interact with them is the same. The code that I just showed you for map, if you just change it to change the type to unordered map, all that code is basically going to work. So they both store key value pairs. A map is a binary search tree. And I just said this, it's log in to find it by key, it's sorted. And in order to use it, your key type, so say we were using strings, it has to define the operator less than so that we can do, the sorting can be done by the tree. Unordered map is a hash table. It's even faster, order 1. It's not sorted. And you can use it as long as something called the hash function for your key type exists. A hash function takes whatever you pass in, a string, an object, an integer, whatever your key is, and basically creates an integer from it that can be used to look things up in a hash table. This hash function already exists for important built-in types. The STL provides it for strings and integers and some other basic types. If you wanted to use your own complicated new class that you made, if you want to use an unordered map, you're going to have to write this function. If you wanted to use a map, you'd have to write this operator less than. Okay. Can you have more than one value? There's both unordered map and unordered multi-map. So it's exactly the same as map. If you want repeated values, you can use an unordered multi-map if you want a hash table with repeated values. Okay, so the standard template library is really big. So we can't teach it all to you. We've just given you a taste of it. The most important part for you to be able to use are these container classes, which is why we focused on that. You can browse what the STL has to offer. So this is the reference that I just clicked on during the class. You go there often. You don't really code by trying to memorize all the function calls. You learn kind of the basics of how you call things, and then you go look it up on demand. Lots of great examples online. Ask on Piazza for help. Okay, and I'm going to do one last demo, and then we're done for today. And this is a short demo. Okay, this is actually, notice I'm using the virtual machine. It looks just like the UG machines if you want to try it out. Okay, so this is basically like the vector versus list comparison we did before. This is now searching, and I'm doing it here with a map. So this is basically a map. In this case, it's using integer keys and integer values, and I'm basically populating the map with a whole bunch, basically 1 million randomly chosen keys and values. I don't really care about the data, but I basically make a bunch of integer keys and a bunch of integer values and put them in a binary search tree, 1 million of them. And then I do 10 million random searches. So I just generate random keys, and I go find, where is that in my binary search tree, and then I don't actually do anything with it. But it doesn't matter. I just want to see how fast this is. I've done this in 2 ways. So with a map and then with an unordered map. And the code is identical, except, this line. We've just changed from a map to an unordered map. Okay, so I want to do a speed test, so I should always use the release build. So I just built both those with optimization, and I use the time command to see how fast they are. Okay, so my map search, I did 10 million lookups of random values, and it was pretty fast. It was like 1.11 seconds, so that's pretty quick. Now let's see what it was with the unordered map. With the unordered map, it was 0.68 seconds. Okay, so it was faster. And for things this short, sometimes it's good to measure them more than once. So I'll measure them again. There can be some, if there was a little bit of time getting it from disk and so on, that can actually screw up your measurements a bit. So I'm just going to measure them twice. And it comes back pretty consistent. So there's not an enormous difference. On this computer, the unordered map is about 1.5 times as fast as the map. It turns out on the UG machines that the difference was a bit bigger, more like 2.5 times faster. But basically the difference between log n and order 1 is not as big, nearly as big as the difference between n squared and n. So an unordered map's faster, it's not as much faster. And that's it for today. So I'll hang around in case there are any questions, but that's the end of the tutorial. Thanks, everybody.